Hello, hello, everyone. Welcome to week number 5. I guess you can hear me. Yes. Can you hear me? AD? Yes,
Yeah, we
thank
can
you.
hear you.
Thank you. Good job. Good job. So the first thing to do is to worship. Let's do worship to our syllabus. So we are here. We spend time on what's the background knowledge of about mechatronics. We did a survey about the definitions of mechatronics. So you can see we don't have a unique, everybody accepted definition of mechatronics. But we roughly know what's that. Okay. After that, we spend time on the basic elements and the components and its connections, and we got the general concept of A-type, T-type, D-type elements. With that, we can leverage our knowledge in circuits. We can solve mechanical circuits so through the linear graph theory. So you go through the linear graph section 3.6 and go through the examples. You should be fine. I have a announcement here. We are not going to have complicated linear graph method for mechanical circuits in final exam, but you still need to practice via the homework, okay? Well, we are now in week number 5. We are going to spend quite a while on signals, systems, modeling, and simulation. Good news is you are already doing modeling and simulation, okay? You are already doing them. So we probably can spend more time on those foundations. After that, we are going to spend 2 weeks on control systems, okay? So as we said initially, control system is to change the behavior of the system to the desirable behavior we wish, okay? Like the room temperature, we hope it will maintain at a certain preset level, like 70 Fahrenheit degree. Okay. There are a lot of aspects on the control system. The most important part is the control system. If you do it smartly, you can make the system to behave nicely as you wished. But if you don't do it correctly, you can make a stable system unstable. This is called destabilize. You can destabilize a stable system. On the other hand, if you do it smartly, you can stabilize an unstable system. So you have an unstable system, if not controlled, and make it under control, behave nicely. So because of that, we need to be aware of the stability. So we are going to talk about that in week number 8 and 9. Very good news is we don't have any lectures lost due to public holidays. So we got enough time to do our job, okay? Let me also show you today's quiz. So you can see today's quiz, we have a small quiz here, okay, about do you still remember how to use Laplace transform to solve circuits problem? So that part I'm not going to spend any time to go through with you, but I uploaded a file. Can you see my screen with the file here? Go to notes, week 5, this one, Laplace transform for circuits. This file please go through them, okay? If you didn't get perfect score in circuit theory, you are not confident about your preparedness of circuit theory, go through a summary of review slides on circuits here. So these two are for you to review, okay? Today, we are going to go through the signals and the systems module. So in the end of the lecture, you should be able to answer all these questions here, okay? Okay, so let's start. First of all, we are going to start something, let me hide the video, hide the floating, this one, okay. Let me do this. So this is our week number 5. This deck of slides is talking about different types of signals. You receive signals all the time, and you send out signals all the time, okay? Your mom look at you, you have signals showing that you're grumpy, that your mom will ask, are you okay, honey? Because she saw a signal from you. So what I'm trying to say, signal is around us everywhere, all the time. So you drive, you see traffic lights. So those are signals. So the whole part of this, we are going to talk about signals, convolutions, Laplace transforms, talking about the copy technique. I'll talk next time. I'll invert initial value theorem, final value theorem for Laplace transform. You can read our appendix B in our textbook, okay? And I hope you are start to know what is delta. We are going to talk about it today. And you should know transfer function. I guess you are already doing this in the lab, okay? And the impulse response. So basically, this is a self-reading module. I'm not going to walk you through all the slides here today. I'll just let you know that usually when you have learned ENGR 065, there's a missing course about signal analysis in our curriculum. The whole School of Engineering doesn't have a course on signal systems. And with this signal and systems, so this a trend, what do you see? It's a trend of abstraction. Abstraction, okay? Abstraction. So remember, I asked you a question about between technician and engineer, where you draw the line, okay? Where you draw the line. I want to draw a line here. So I draw a line with Laplace transform. Okay, because as a technician, you never need a Laplace transform to do any type of analysis. You don't go MAD, modeling analysis design cycle. Okay, just put your hands, get the fix done. That's technician. But however, you do a modeling analysis design cycle. That's engineer's work. Okay, the foundation is Laplace transform. So learning how to use Laplace transform solving circuits, you need to go through that deck of slides. Okay. All right. So today we are going to talk about signals and systems. Basically, we are talking about dynamic systems. Dynamic systems. So signals and systems and types of the signals and random signal, deterministic signal. So if people ask you, what's the opposite of random? Okay, what is the word opposite of random? It is this one, deterministic, deterministic, okay? Then you have continuous time versus discrete time, okay, discrete time. And then use MATLAB. This part is actually you got enough training since the beginning. So there are so many different types of signals. I don't want to go through. Even dog's bark is a signal to you. Anyway, a system is, you know that you should have a purpose to talk about a system, right? So your system, you have a stimulus in and a response out. So excitation and a response, okay? So types of signals, continuous, discrete time, okay? You have continuous time, but discrete value, and so on and so forth, okay? And so only this part is digital signal. It's based on 0 and 1 sequence of them, okay? So, but there are many others, okay? Others. So, and there are some very noisy random signal, and you have digital signal with randomness, okay? So as you can see, why we usually prefer digital, because it is more immune to the noise, okay? Immune to the noise. So for deterministic continuous time signal, like sinusoids, period, frequency, peak, amplitude, all these things, I think is standard. However, in discrete time, you have different ways. So you can see this is a plot with a dot and a vertical line towards the x-axis. So what is the name of this type of plots? So in the MATLAB, you use the plot, right? Okay. I want you, so you plot something x, y, something. But do you know that there's something called stem? If you haven't tried that, you should try it. Then they will give you plots like this, okay? There's also a command that's called stare. This is something like this. This is a stare, okay? Try. So these are the alternatives to plots, okay? And the signals is function of space. You could have, so this one is called a 1D signal, okay? Only change versus time. And this is a spatial variables, x and y coordinates. So do you guys see something inside here? Do you see a gun? Yeah. So, but from here you don't see, right? So, but you do some sophisticated image processing, then you'll see a gun in here. Okay. So that's very interesting, right? So there's a dedicated course on image processing. How about the face recognition? If you use iPhone, they use a Face ID, right? Face ID. They do this type of processing all the time and customize the features of your face. So this can be used as the password to turn on your phone, okay? Use of MATLAB is extensive. I hope you will start to use it, okay? And faculty center, mathematics. So how to describe all those signals in the math. So these are signal types, okay? And I'm not going to go through this one, okay? So all different types of signals. So this signal, I want to say something here. So this is actually called, you have points in here, but you have lines connected. So this is called piecewise continuous, piecewise linear, okay, piecewise linear. And this one is called piecewise constant, okay, piecewise constant, okay, piecewise constant. This is piecewise, piece by piece, piecewise linear. So this is called sampling. So it's called sampler, okay? So you have a continuous signal in here, then you got a sequence of these, okay? So this kind of sampling, uniform sampling. So you have a sampling frequency. We are going to do digital control side after spring break. We are going to talk on this. So this is the sampling. So I'm going to stop here, okay? I'm going to stop here. So it's actually very interesting. I want to show you something. So this is called unit pulse, okay, unit pulse. So unit impulse. So you make sure the area in here is unit, is 1, okay, is 1. So if you send A to infinity, send A to 0, meaning the width here goes to 0, then you can imagine the magnitude here will go to what? Go to infinity. So this thing is called delta T, idealized unit impulse, ideal unit impulse. So I'm going to talk about this ideal impulse later. But today, let's focus on this deck of slides. So our philosophy here is, okay, our philosophy here is focus on continuous time signals, okay, continuous time signals. And we are also talking about continuous time systems. For discrete time, we are going to do in the week 11, talking about digital control, okay? So from now on, I wish you are going to read the whole deck of that signal slides, showing you different types of signals. But we are going to focus on discrete sampled data. So for computer control, we have digital control. So before that, we focus on continuous time signals. So signal and systems. Signal is signal. System is signal is a signal. But a system is a signal in and signal out. So this is also called a mapping, okay? So a system, the system is a mapping between one signal to another signal, okay? So a signal is a signal, okay? A signal is not a system, okay? A system is a mapping between one signal to another signal, okay? So you basically operate on one signal and you generate another signal, okay? That's system, okay? Signal in a controlled system, mechatronics system point of view, you should think about your home thermostat. You have set point, it can be input signal, disturbance signal, or measurable signals, okay? So those properties like analytic, sinusoid, standard deviation, all those things. So systems is a process, okay? It can be a sensor itself is a system, but it can be a subsystem of a system, and so on and so forth. So for mathematically, how you describe that system, you can use differential equation, transfer function, and state space model. So we have learned this state space and differential equations, okay? So we are going to focus on the continuous time, and sampled time we are going to do later. And we're going to focus on linear. We're not going to do nonlinear. Nonlinear is a separate course. It's ME142Sp21. Actually, I'm teaching this course this fall semester for graduate students. In fact, if you are interested, you want to challenge yourself, you have enough bandwidth, you should sit in the class. I'll allow you to sit in, okay? Because I had some good experience for our seniors, undergraduate students in the graduate course. Turns out they did so well. I'm impressed. So we are now starting to talk about. Let me see if I have a chat. Okay, not yet. How you can block the signal? You need to talk about what signal should be blocked. Okay, so you want to allow some part of the signal in, some part of the signal out, some part of the signal stopped. That is called band pass filter. Okay, band pass filter. If you can also talk about a signal that you want to chop off all the negative parts, I only leave the positive parts. How do you do that? You use a diodes, okay? Use a diodes. So if you have diodes, so you only have positive to go through the diodes. Negative ones you cannot get through. See what I mean? Those diodes. Okay. So what we are going to cover today is starting with a high order differential equation and talking about Laplace transform to put differential equation to algebraic equation. So this is the beauty of Laplace transform. Then how we can tell the whole system is stable or not. And also we need to talk about frequency domain response. Okay, especially for the Bode plots. Okay, but not this week. Yeah. So this is our starting point. Okay. Remember, we have gone through some type of differential equation, usually without this term. Okay, without this term, it's only with a B0U. But what if you also have other derivatives of U? But remember, the U derivative is at least one order less than the highest order here. Did you see that? Yeah, there's a reason why we need that. Okay, we need that. So let's do that. So at this point, I want to show you, show respect to Heaviside. This guy is very good. When we call a step signal, this is one. This step signal, unit step signal, we call this as a Heaviside function, okay? So to show respect to Heaviside. Do you know why Heaviside is great? He is the person to make the Maxwell equation looks like today's form, okay? Today's form. The original Maxwell equations are simply messy, multiple pages, okay? Heaviside made it just four equations, okay? He made that, okay? So great. And at his time, he also invented this idea so that he can turn the differential equation into algebra. This is algebraic equation. So then simply introduce something called the d dt equals rho. So it's a symbol, okay? Rho is a symbol, or simply an operator, okay? Operator, abstract operator. So it's funny that he used this method to turn this one into algebraic way, and they can solve the differential equations and get correct answers. But this type of notation at his time, nobody supported it, and everybody is questioning him or even criticized him. And one day he gave a talk and he said, the results are correct. So You complain all the math's not rigorous. He said, if you do not, no, sorry, he said this way, do you refuse to eat because you do not understand the complete mechanism of digestion? So, so you don't refuse to eat. You eat, even you do not understand all the digestion process. He made a good point. Okay, and it's surprising to me that you check into the literature in his time. He even talked about square root of this rho. Okay, square root of this rho. This is as if you are saying that you have d 0.5's derivative. Okay, so this is actually a half order derivative. It's a fractional order calculus based differential equation. So our Mesa lab is among the top group in the world on this type of topic when differentiation and the integration is of non-integer orders. If you want to know more, you can talk to me. Last semester, I offered a course, okay, called Fractional Order Mechanics. Okay, this is the only case in the world we officially offer graduate level course on this topic. We are the only university in the world. Okay, and we had 2 undergraduate students in the class. I feel proud of their achievements. But anyway, we come over here. You can see we have a polynomial of rho, here. We can extract the yt in here. So that's the precursor of Laplace transform. Heaviside already did that. But Laplace transform made everything the solid foundation. Okay, now it's time you fill up your quiz. So this is the real definition here. One thing I want to draw your attention is something called zero minus. Zero minus, okay, zero minus. Everything before zero minus, okay? Zero minus means 0 minus epsilon, and the epsilon is so small. So at zero, or 0 little bit before 0. So it's called 0 plus, okay? 0 plus. So anything before 0 minus is called initial condition, okay? Initial condition. So we have to consider that initial condition carefully when you do a Laplace transform. This is the inverse, it's a complex integral. Usually you don't use that. You usually will be giving this one. What is LUT? Have a guess. Look up table, okay? Look up table. So usually you do this inverse Laplace transform using a lookup table. And in the final exam, in many of the exams, you usually will be giving a table so you can use it. You don't have to memorize all those things, okay? So one of the key results is derivative of function. So we usually call this is yt y of s. This is called a Laplace transformation pair. Okay. So you probably heard that yt is ys, Laplace transformation pair. Then I wish to know what is the ddt yt. So is this correct? Ys. So this is in general correct if this initial condition is 0. But if it is not 0, you have to put it here. You have to put it here. Okay. If you don't put it here, you are wrong. Just give you an example of your capacitor, okay? Give you an example of capacitor. So you already have something stored in a capacitor. Then you turn on, so that initial condition of the capacitor is 0 minus, okay? So let me say this. So you already have a capacitor. So you already put this one as a DC source. So there's a 10 watt DC. Then you start to charge this one, right? After you charge it a long time, this is fully charged. So you start to put this thing, turn on this one. So this is 1, this is 2. Put on 2, then you have R in here. What's going to happen? So you are going to discharge. So why you have discharge? Because the voltage in here is already charged. So that when you turn on here, then you have an initial condition, okay? So that's one of the physical meaning I show you, okay? So this is a typical Laplace transformation table. So you have a 1, you have a 1 over S, then region of convergence is sigma greater than 0, and on the right-hand side on the complex plane. So this is a unit impulse. So then its Laplace transform is 1, okay? Is 1. If you have t, then it's 1 over s squared. So if you have tn, so you have n factorial s. So, but question is how you can how you can do this. So, what is the definition of our in here? So, it's a 0 minus to infinity, and f of t e minus tau s f tau, sorry, and d tau, right? So then you have s left, okay? S tau, y tau, d tau, okay? S tau, y tau, d tau. So, but right now, my f is 1, okay? Put the f is 1 in here. So basically, I'm doing this thing. Okay, all right. So this one, you know how to do it, is a minus tau. So you do this one, so you have a 1 of s, okay? Okay. D E minus tau s, okay? Then you do this same thing here, okay? All right, s is constant here. Tau is something we care. Okay, so because of that, I have a 1 of s in here. Then I have a e minus tau s in here. Then I have minus 2, 0, okay? So let's see what's going to happen. So when tau is infinity, this is 0. So it's 1 of s in here, 0 minus. When tau is 0, so this is 1. So this is a 1 of s. So this is this guy, right? So I derived it for you. So in fact, you can derive every entry here, okay? If you are asked to, you should be able to start from this definition, okay? But fortunately, you don't have to. You don't have to, okay? You use this table so that you don't have to rederive this table, okay? But we used actually an assumption when tau is infinity here, okay? How to make this one 0, then s has to be greater than 0. So that's why this is the domain. So the domain. Only when this is true. But if this is not true, so if s is less than 0, then you cannot be true. This cannot be 0. All right, so there are many Laplace transformation tables. So this is a table of some typical functions. But what if you have properties? So this is called linear combination. We already gone through this entry called derivative law. You have high order, then you have s to the power of k. Then all these are the initial conditions of order less than k minus k. Okay. Integration, you don't have an initial value problem. See, you just 1 over s. Delay is this. So I want to draw your attention. Delay, you have to write this way. Okay. This mu t is actually called a Heaviside function. Heaviside function is this unit step function. So mu t is like this. So the mu t minus 1 minus tau, it is actually this way. So it's tau. So you have this one. This is 1. Everything else is 0. This is 1. So this is mu t minus tau. Okay, so this is tau. Okay. So when you have delay, you also need to have this yt delay and times mu t delay. Okay, then you will have this e to the power of s minus s tau. So this is a delay. Okay, there are many other properties. One of the properties, the t times yt. Let me see, what's your question? This is the unit step. Yes, it's unit. This is all unit. Yes. Yeah. And convolution. I understand many of you probably didn't know this convolution here. Okay. But final value theorem, initial value theorem, you should have learned. Okay. And if you have a e to the power of et weighted on this f of t, then you'll have s minus a. So you have convolution in time, you have a simple multiplication here. You have a multiplication here, you have convolution in frequency domain. Okay, so these are not very commonly used. But most commonly used is final value theorem, initial value theorem, derivative law, integral law, okay, linear combination, and maybe time delay, okay. Okay, so given that, well, let's try to do this side. We do Laplace transformation for differential equation in the following algebraic equation. What happened? What's wrong in this? So as I said, you have a n's derivative. You have Sn. Where are all these initial conditions? Where? So the initial conditions are actually lumped inside here. Okay, related to this initial conditions, but those are usually ignored because we assume all the initial conditions are 0. Okay, yeah, 0. So then you can see we have g of s. There's u of s. You pull out all the u of s. Okay, all the y of s you pull out. This is the same idea as Heaviside. You turn into a polynomial, and you do division. So this is equals, so output divided by input. Okay, so you have a polynomial here, a polynomial here. Did you see something different? So this is not an, okay? So an is 1, okay? An is 1. So this is because if it is not 1, you can become the 1 divided by an, both numerator and denominator. So we just simply say this is 1. So this polynomial is actually sometimes harmonic. The first highest term is 1. So g of s is called transfer function. It's very easy. So I have u in here. Sorry, I have u in here. Through this transfer function, I become y, okay? So this is g, okay? So u times g will give y. So that's why it's called transfer function. So in this transfer function, you have a polynomial of s, and a is one order higher than the b polynomial, okay? B polynomial. And in our MATLAB, we can already do this giving A, giving B, then we can do this. So this is a MATLAB prompt, okay? So you can just do a TF. So you do a so basically you have a numerator, denominator, right? So you have a B first. So bn minus 1, comma, then you have 1, then you put another a, put a 1 in here, then you have an minus 1, then this will give you this. So this TF will generate something called LTI-OBJ, object, okay? So linear time invariant object. If we do state space, then we can write down, this is initial condition in the state, okay? So then we have AX, B, C, D. So in the end, we are getting, can solve the Y in terms of my X, okay? In terms of my X. In terms of my U, sorry, in terms of my U, okay? All right, because X is already through here, I can solve the X is S. This is an identity matrix minus A, and on this side, you do inverse, you have x0, then you have this same inverse and B times U. And put this X into here, so you are going to have this guy times plus D times U. This is due to the initial conditions, okay? Initial conditions. So we call, this is G of S, okay? This is G of S. It's the transfer function, okay? So be careful, let me emphasize here. If you have a B, C, D state space, by the way, in the MATLAB, you can use the state space command. Transfer function is, so there are two different ways to do that. But remember, this one, giving A, B, C, D, you get a G of S. This is unique, okay? This is unique. But giving G of S, you convert this A, B, C, D is never unique, okay? So this actually is called A realization, A state space realization, okay? A state space realization. Time delay, okay? Time delay. So if you have a signal in here, you have a, say for example, you have a X signal T in here, going through a black box, what you get out is XT minus tau, right? So this is called delay, okay? This is delay, okay? How this is possible in computer? It's possible, let me tell you. So if you have a buffer in here, so this is XT. So whenever you have XT come in, you put it here. And you maintain XT minus 1, XT. So you XT minus 2, minus 3, minus 4, you maintain a buffer, okay? And every time you get the last buffer, it's XT minus N, okay? Get out. So this is getting, you get a new one coming, you pop out another one. So what's left is this always N length of the buffer. So this can be used to digitally mimic this delay to have this first in, last out, first in, last out buffer, okay? So it's a delay. But this delay is in computer buffer point of view, but in reality, it's always true you have a delay. Say, for example, you have a pipe, you have a fluid. So you turn on the valve, the fluid will take time to transport a certain distance, then coming to that end. So usually the delay, sometimes people in industry, you call transport delay. Okay, transport delay. Okay. So it's due to that you need takes time to go from here to there. So it's transport delay. Yeah, transport speed. So here's an example of a heating system. So you have motor, take a fan, you blow this one, then you get air. This is like your air blower, a hair blower to dry your hair dryer. Okay, but if you put a sensor in here, so the air from here to here need time to travel. So there's a delay. Okay, there's a delay. And you have a signal here. So this is a signal you measured. You said, oh, this is my temperature. Why is my temperature? But it's only temperature on this point. But what about the temperature in this point? Okay. So then I should be T minus tau. Okay, T minus tau. Okay. Maybe also the amplitude is also different, maybe K. But that shows the delay idea. Okay. All right. So here comes to one of our questions in the quiz. So you can see this is like this is called first order system. So K is a gain. K is a gain. Tau is a time constant. S plus 1. Okay, so this is a first order system. It's actually a low pass filter. So you cascade this one with TD is my time delay. So this together is our HFS. Okay, HFS. So from here to here. So this is a temperature seen by the thermocouple is approximated by the form of this one. So it's like this system. Okay, this system. Okay, so this one is called first order. So this is the first order. Okay, plus delay time. FOPTD. The first order plus delay time. Why we single out this thing out? Okay, here's the reason. So in all industry control tasks, okay, among all control tasks, 80% or more are for temperature control tasks. Okay, when you do temperature control task, and your model can be well described by the schematics here or by the FOPTD. So in FOPTD can work for 80% of all your control application tasks. So that's why we should pay attention to this type of systems, okay? So if you are in the interview in industry and people throw out a 5-letter abbreviation, say, oh yeah, can you tell me what is FOPTD? And you say, sorry, can you say again? I don't recall. I think you are going to fail your interview, okay? So I'm teaching you now FOPTD. What's that? First order plus delay time, okay? Then in the final exam, if I give you an abbreviation FOPTD, you don't know what's this, what kind of message you are giving me? So That's why I put in the quiz. All right. So at this point, we can see that we are far away from those components. We are already living at G of S, G of S. And among all the G of S, okay, one of them is particularly important is FOP delay time, okay, which is K over tau S plus 1, E minus L, another tau D times S, okay? All right, so, okay. So we're talking about stability. So the key question is you need to have the idea of zeros and poles, okay? Zeros and poles. So to understand that, we need to study impulse step responses. Let's talk about Dirac delta is this thing, okay? And then be careful, you never write delta t alone. Delta t is not a well-defined function. So what we know about delta t is delta t is 0 when t is not 0. But when t is 0, this is not 0. It's not 0. It is 0. So is this infinity? I don't know. Perhaps, okay. So this is called special function. It's not well defined. All we know is minus infinity plus infinity delta of t dt. It will be 1. Okay. So together defines delta t. Okay. Together defines delta. So delta t is called generalized function. So let's start from here. Remember, what is the arrow in here? 1. Okay. Steady state response. So that is impulse. Then you send delta to 0. Delta to 0. Then you end up with delta t. Okay. So that's why people write delta t like this, boom, like this. So this is, but this is you have a t0 in here. So this actually is called delta t minus t0. This is 0 when this is non-zero. So all 0 is when this is non-zero. So if it is not 0, it is not 0 at 0. Okay, at 0. So not 0. This, I don't know, maybe it could be infinity. Okay, but they should not understood it that way. It's integration as 1. So steady state step response. That is when you send t to infinity, you write. So sometimes people write SS. Okay, steady state SS. Okay. So this is a final value. This is a final value of y. So how this is a final value theorem. Okay, final value theorem. So we are talking about step response. So basically, I have step in here, get through the system, which is g of s. Then what you get is y of s. Okay, y of s. So y of s is g of s times you have a unit step. Laplace transform is 1 of s, so it's 1 of s. Okay, so this is this is y of s. So, but according to the final value theorem, you need s in front of it. So s times ys, send s to infinity. Okay. Oh, no, I think this is wrong. Send s to 0. So this is called initial, it's called final value theorem. Then you send s to 0. This is a typo. Okay, I'm sorry. This is 0 in here. So then you cancel out this s. then what you get is G0. Okay, G0. Okay, so the transfer function here, okay, G0 sometimes is this G0 has a special name. It's called DC gain. Okay, DC gain. Why? Because the input is a DC. Okay, it's not arbitrary input signal U of t. It's just a constant. It's direct current constant. So then, what is output? Output is just what you put in here times the DC gain is your steady state. Make sense? Yeah. So this is called steady state or step response. Okay. So here's the step. This is step. This is step response. Okay. All right. So at this point, for a system, okay, for a system, we define some very important indicators. So the 5 of them, okay. Steady state value, y infinity, rise time, overshoot, undershoot, settling time. So let's see. So you have a step in here, then your system will respond. So when t goes to infinity, this goes to y infinity. So the first one is y infinity. Second one is the rise time. The rise time here is when you have 90% of the steady state error. So the KR is like 90%, okay? You get 90% of the y infinity. So that you rise to there is called the rise time. So this is second. So the third one is overshoot. So overshoot is you come over here, you pass this steady state, this one. So basically is this value, okay? It's MP plus y infinity, okay? So usually it's in the sense of MP, in the sense of divided by y infinity. This is called overshoot percentage, okay? Overshoot percentage. Anyway, so in many of the industries, so this could be like 5%, 10%. Okay? So this is the third parameter. What is the other parameter? Settling time. Settling time, you need to think about what is this interval, plus or minus delta. This usually is like 2% versus 5%. So you need to specify, you are talking about 2% plus or minus 5%. So therefore, you get in, everything start to inside here without getting out, okay? So that corresponding to the settling time, so number 4, okay? The number 5 is something strange called undershoot. Undershoot is a number 4. This is the number 5, sorry. Number 4 is called undershoot. So this is undershoot time, okay? So you can see I give you a step is along this direction, but you guys go opposite direction, okay? So this is go opposite direction, even if I give you a right direction to go. So I'm not sure your doggy will or sometimes do this. You ask the dog go that way, it will go this way, opposite way, then come back. So what system can come to this behavior? So this point, this type of behavior is also called non-minimum phase behavior. Non-minimum phase behavior. Non-minimum phase. I'll talk about this one soon. So non-minimum, this is called non-minimum phase behavior. So why there's a non-minimum phase behavior? Let's take a look of transfer function. So remember, we write a B polynomial, A polynomial. We can solve its roots, okay? And written in the product form instead of polynomial form, okay? So this is a polynomial form, this is a product form, okay? So in MATLAB, you can use a TF, okay? You can TF to input this form. Well, what if you have this one? What is this one? So actually, MATLAB has another command. It's called ZPK, zero pole gain, zero pole gain. So you can get this product form. Then you use this polynomial form. You use this. Okay. So in this case, numerator is called 0 and denominator is called poles. So you can see that m usually is less than n, So, but n minus m is called a relative degree. Okay. So in our quiz, I give you a transfer function. I check you what's the relative degree. You should know it, right? The answer is 0 because n equals m equals 2. So whether your quiz is correct or wrong is not important. You put it in non-empty is important, okay? So I'm not to grade every quiz, it's just too much work. But I'll count who didn't submit. And I'll quickly go through to see who didn't write anything on it, okay? I'll red flag it. So you know the concept of relative degree? Yeah. Let's talk about poles. And so in this one, you have a pole, okay? You have a pole. We're going to talk about this one later, okay? We need to go through this non-minimum phase pole quickly. So talk about zeros, okay? Zeros. So in this case, very interesting, okay? So I put a minus s in here, okay? So you can see why they put minus s here. What's the reason? The reason is, do you see this is strange? They also put a c in here. Why? The reason is I want to make sure my DC gain is 1. Okay. So when you have a DC 10 watt coming in constant, my output is also 10 watt. Okay, constant, because the gain is 1 here. Okay, this is for convenience. Okay. Make sense? Now, this is going to be interesting. We give this guy a step. Put the H in here, give you a step to see what's going to happen. Okay. So you can see that if I give you a step, okay, give you a step, the step on the step response, okay, step response. Okay. So it should, okay, remember, this is -4, -6, -2, this is 0, okay? So this is 2, this is 4, this is 6, okay, according to that. So here, actually, I end up with 1. Because I give you 1, you end up with 1. So because my H0 is 1. But if I choose different C value, if I choose my C as negative ones, okay? So C is negative, it will go this direction, okay? Go this direction, okay? So if my C is negative, because the C is negative, in the end, okay, I'll come to 1. But in the end, because of the S is minus here, so initially this minus and this minus will cancel out. So as if when C is negative, say for -1, then I end up with S plus 1 and S plus 1. Let's do 10, okay, do 10. So I have 10 in here. 0.5 s plus 1. So you see what I mean? So if I have minus, so you have minus 10 in here, you cancel out the negative sign. So everything is positive. So everything is positive. So positive. So the 0 actually affects my transients. Okay, transients. Can you see that? But if my put C is, say for example, I put C is 10. Okay, what I'm going to get is S minus 10. Here I got a 10. Oh, no, minus S plus 10. So you have 10, S plus 1, 0.5 S plus 1. Okay, so this H of S when C is positive 10, okay, positive 10 or positive 0.1. So you can see it will not go this direction, it will go opposite direction, then goes to here. So this is undershoot, okay? So this is undershoot. This is undershoot. And this is overshoot, okay? Overshoot. So undershoot and the overshoot is because of the sign of your 0, okay? 0. So in this case, because of this 0, S is 10, is a 0 that is living in the complex plane real part and the imaginary part is living in here. So this side is called RHP, stands for right half plane. So if the 0, usually 0 is using this circle. If the 0 lives in the right half plane, okay, then it will result in the undershoot, okay? So this undershoot behavior, as we seen here, is called non-minimum phase behavior. Why? It's because this will cause a phase response non-minimum. So therefore, we don't call this pole. So this pole living in RHP is called non-minimum phase 0. In many books, papers, they call this as unstable 0. I think it's wrong, okay, strictly speaking, because stability has nothing to do with the sign of 0. So as you can see, the 0 in here can be positive or negative. It didn't affect my stability. Stability means what? If you are unstable, you will blow up. So in our case, we are not blowing up. We are all convergent. So this is also an example showing that the system stability is not determined by zeros, no matter it's positive or negative, no matter the 0 lives in right half plane or left half plane. Doesn't matter, okay? Left half plane. Doesn't matter. You can be here, but if you live in here, you have overshoot. If you live in here, you have undershoot. So that undershoot behavior, if you want to be taught as an expert in control, never use unstable 0, please. You only say, oh, this is a non-minimum phase 0. You insist saying that way, people will respect you. Okay. Okay. So you get it? All right. So we already said that the stability here is linked to my pose. Okay. So it's actually in this slide. Stability. System is stable if any bounded input produce a bounded output. It's called BIBO. BIBO. Bounded input will produce bounded output, so BIBO. This is very basic, okay? You don't have a bounded input. You gave me an unbounded output, meaning the output can go to infinity, unbounded. Okay, that's very bad. That's basically an explosion, or smoking, or fire. Okay, so we can actually use a PFE. So here is the first time we talk about PFE. In the future, you should remember that. PFE stands for partial fraction expansion. I'll do one for you now before we finish. So you decompose total response into response for each pole taken separately. For continuous time system, then we will be able to see the poles strictly negative real, okay, in the open left half plane, LHP, on a complex plane S. So continuous time system, the stability bound is the imaginary axis. So that imaginary axis is here. So basically, you draw a bar. You draw a bar in here. On this side is stable. I mean, the poles live in this side. This side is called left half plane. Then system is stable. If you live in this part, then it's unstable. Okay. So let's go through this example then where I'll let you guys go. So this is the simplest first order pole distributes like H1. So you have this is called first order system without delay, okay, without delay. So you apply a unit step, which is 1 of S in here. This is your step, U of S. And this is the original H1 of S. Add together, you want to find out what's your step response Y of T. So you add this multiplied together, you split this one, you get these two terms. So this split this one into two terms. This process is called PFE. It's called partial fraction expansion. Okay. So you want to do inverse of this one. So you do inverse of this guy. We know this is the K mu T. This is a heavy side. Okay, heavy side. And if you do this one, these are constants. So this is exponential according to the Laplace transformation table. So this is exponential. Okay. And you do the pole is S plus 1 over tau divided by K. So then you have a K get out 1 minus this one. Okay, minus this one. So basically, you can see what is the H0? It's K. So in other words, if my input is 1, okay, what is my output? My output, when T goes very big, it is not 1, it is K. It is K. It is K. But initially it is 0. Y is 0. So it will eventually goes to K like this. So this is my YT. This is my UT. Okay, my UT. So this is exactly true. When T is 0, this is 1. 1 minus 1 is 0, so it's here. Okay. So T is 0. When T is infinity, this is 0. So 1 minus 0 is 0, so it's K. All right. So this is interesting. So how do you know this is a K tau in here, this is a K? So I do know I have this part and this part. So what if I have many terms in here? I have cascaded. So you have a step in here. So then I have, so this is 1 of S in here. So you have K tau 1 S plus 1. So this is K1. Okay. Then I cascaded one more, K2 tau 2 S plus 1. Let me do one more. That's a K100. I have 100 of these things cascaded. Then I got a Y of S. So then you have 100 things multiplied together. and how you can split all these things out. Okay. I'm going to teach you a very important trick next time. So this trick is called copy. Okay. Copy stands for cover up and plug in. Okay. Cover up and plug in. So even you have 100 of such things cascaded and multiplied together, you still can easily do the job. Okay. Easily do the job. The question here I saw from Daniel is what's the difference how close you get to zero converge? Oh, that is a steady state. Get to the zero converge. I do not really get this question, but if you're giving a polynomial, you give a polynomial, you solve the pole, so solve all the zeros. You can use MATLAB command called solve. Okay, get all the roots. If it's in the denominator, it's called a pole. It's in the numerator, it's called zeros. If the zeros is positive, then it's called non-minimum phase zero. If it is left-handed negative, I mean the real part, I mean could be complex conjugate. If the real part is negative, then it's called a minimum phase zero. It's a regular zero. If you live in the if you live in the right half plane, so that's called non-minimum phase zeros. We're going to continue this topic next time, so we are over time. Good. I like this interaction. Okay. Is it the difference how close you get to zero converge? Yeah, we'll discuss this one again next time. Okay. If you don't have any questions in the chat box, I'm going to stop this here and finish today's lecture. So let me see one more. Have good. Okay, thank you guys. Thank you. Happy Year of Ox. Okay, bye.